the scientist D, and he is also associated with other various profiles within the government as well. So his name is Dr. Muheet, and he will be delivering the as talk on in this particular FDP regarding IoT and 5G. I welcome you, sir, for this.
Thank you very much. Okay, we'll start.
Yes, you can start, sir.
Am I audible?
Yes, sir, you are audible.
I'm audible, huh?
At least respond among the participants. Please respond. If you are facing any sort of problem in audio, video, please share with us that we are having some sort of issues with this particular setup. You can continue. Yes, you can, sure.
See, thank you very much for inviting me on this session. My topic today will actually be database in Internet of Things. It actually means this seminar has been dedicated to these IoTs. Therefore, I need not to stress on more IoTs. But actually, I will be giving you an sort of insight of the databases in IoT and in Internet of Things, and why these databases are used, why data is used in IoT, and how this data drives IoT devices, whether it is a car, it is a homemade device, or it is a bulb or anything which where you are using these IoT sensors, whether it is a human body where you have what you call as that's called as a BAN, that is a body area network, or in healthcare or anywhere, means the data means whenever we know that if an IoT device has to take a decision or has to actually what we call as an intelligent IoT devices, the data, whether even if they are not intelligent, still the data for IoT is very important for communication, for say if you just say start from a sensor to a very big analytics of the data. The data has a very important role to play when you have IoTs. Now, actually, what about saving of this data? How we are going to store this data? How this data can be retrieved? How this data can be accessed? Whether this data is fast, which data is where we need to have what you call as consistency, where we need to have what you call as what you call as availability of data, or we can also say that where the data can be fault tolerant, and the other things, because these IoT devices are normally very robust, and the data which actually is going around these IoT devices has to be very needs to be very what you call as we need to take care of this data in a very sort of in a very better manner. Now, in today's lecture, I will be discussing about what are the various databases that we are going to use in IoT, why there is why we have to select different databases for different IoT operations, and what are the various types of databases that are available for these IoT devices, and based on the usability of these IoT devices, and how we are going to store, and what will be the difference means if you just change a database for an IoT, and how it is going to impact the IoT device, and it is how it is going to improve our response time, and obviously affecting the latency also. Now, before going, everybody knows that IoT devices are nothing but it's actually the network of physical objects, where where they are all is the internet is very important. Means unless or until you don't, these devices are not connected to internet, they are not IoT devices, because internet is missing. Now, actually, how they are embedded in any device. They can be put, say, for example, if you want to make an intelligent window, intelligent door, anywhere, you have to embed these devices. Actually, these devices are basically there are sensors, and these sensors can be what you call as a motion detector. These can be temperature sensors. These can be any what and all means sense of smell, sense of touch, sense of taste. There are for everything you have a sensor, and obviously these sensors will collect data for you, and there has to be a software which actually will take this data and and obviously use this data for transporting, for analytics, and many other things. And obviously there are adjoining technologies which actually help of implementing such things. Therefore, this IoT is actually nothing, is a device. It describes a network of physical things that are embedded with sensors, software, and other technologies for the purpose of connecting, sorry, exchanging data with other devices. Now, if you just see the predictions for IoT, this is the, you can see the data, which is actually no doubt we have this IoT, that is the revenue, and this is something like cellular. And here, this is very important that there is a 2 zettabytes of data. Therefore, it's a huge data which will be generated from these IoT devices. And this data has to be what you call as, if you really want to make those devices intelligent, this can be a real-time data also. This data has to be utilized in a best possible, in a best optimized way, so that the what you call as the decisions that have to be taken from these data, the commands that are optimal, and they are done in a way, the way we have designed, or we have made these sort of these devices. Now, if you go with the what you call as the basic IoT platform, we see that no doubt the keeping in view the security measures which we already take in these devices. We start from the hardware connectivity, and then we end up in services and user application interfaces, where directly the users can either they can operate on the device or take certain decisions based on the data that is available from the device. And that actually sits on, that is very important, that here it sits on this application layer. Now we know the sort of, just an overview I'm giving you about the IoT in agriculture. Means you can use IoTs in what you call as in agriculture, in embedded systems, and wireless biological. Now, these are the technologies which actually have made this IoT possible. That is, obviously, it is access to low cost, low power sensor technology we have. We have a wonderful connectivity. And obviously, when these IoTs are placed on the clouds, and we are using a cloud interface for running these IoT devices, therefore, we have cloud computing platforms. Obviously, when we have a huge amount of data with us, and we want to make those machines, those cars, those fans, those bulbs intelligent, obviously we are going to use certain data mining and machine learning techniques for analytics and for knowledge extraction. And obviously we have a conversational artificial intelligence, like you have what you call as Siri or Alexa and all that, where the devices are actually now talking to you, and they are getting data for you from internet. Now, basically, there is now, this is the main slide that which actually determines the logic behind our lecture. That is, the first of all, let me make you understand that whenever when we work on what you call as IoTs, there are two challenges, rather two kinds of databases that we use. One is called as a static, and one is called as a streaming database. Whenever we say static databases, that means we have a database where data is at rest. Means we are not using the data is at rest. And obviously, we store data in the form of what you call as we store the data in the form of what you call as the relational tables that we'll be discussing later in this lecture. But you have to understand one thing, that there can be another, because once you have, for example, you have say 5,000 devices, and 5,000 devices are connected with internet, and they have all IoT sensors installed in them, and they are actually giving you some data, for example, some temperature data, or some pressure data, or any data there. They are continuously giving it, and that we call as a data stream. Therefore, data can be very static, it can be at rest, but data can be in motion also. Therefore, in both the things, in IoT devices, we can have data at rest, we can have data at motion. Therefore, whenever we have data at motion, so obviously acquiring that data is, say, if it is at rest, no doubt means, the data is periodically added to the database is one thing. But when data is continuously being retrieved from that sensor, and it is continuously being added to the database, obviously it is a big challenge. Therefore, when we talk of these static databases, now why to use this static database, why to use this streaming database, that we'll be discussing in our lectures based on whether we want to make this data consistent or we want to make this data available. What is the consistency of data? Consistency means, say, for example, you have a financial data, you have a stock exchange data or anything. The data there, it has to be consistent. Consistent in the sense that means the A at the end of the transaction, we should be in a position to know that after the transaction is ended and all have done their work, there should not be inconsistency in the data. Means data, say for example, you have updated a record, then you have modified. Of, for example, three people have updated the record. Say one has added two, another has added four, and another has six. That is 2 + 4 + 6. That is actually 6. 6 is 12. Therefore, the value of 12 has to be added to the database. If that has not been added, then obviously we can say there is an inconsistency. But when we have a streaming data, therefore, normally what we do, we have a continuous data, and storing that data is obviously a very big challenge. Therefore, normally we don't go with the main intention here is to collect all the data. It's not, consistency is not a challenge there, and availability is the challenge. And availability makes the data, for example, means we have say full day you are connected with your, say there are 600 odd devices and they are giving you the data. The main challenge is the all the data that has been released by every device, has been sent by every, has to be stored in the database, and there has to be no, there should be no fault. And something like that, there means all the data items what are there released by these sensors should be stored in the database. That is the big, therefore the big challenge for static database is to make it consistent, and for the streaming database it has to make it available. Now, what are the various requirements of databases whenever we talk of IoTs? Number one is, that is because we are working with a very huge data. Means every day, for example, say if you are having a 6,000 for we are having 100 or 200 IoT devices, it can be a lot of that means at least say 1 GB or 2 GB of data is generated, or it is all textual data. Therefore, it has to be high availability and fault tolerant. Means there has to be what I was already discussing. It has to be available and it has to be tolerant. And then, obviously, when you are performing great, you have a huge millions and millions of operations. There is a read and write operations. Obviously, that have to be performed. And for example, having a read and write operation at the same time, you have to access the database. Then you have to see whether, for example, if you are checking for a record or then you are saving a record, obviously it is a huge what you call as huge challenge for any database, because there is a lot of chance there can be some data items may not get written into the database, or there may be huge data loss. Therefore, that things has to be kept in mind whenever we go for a database requirement for IoT. Obviously, there is a time series data and operation support. There is a time series data, and these data are actually, we call them as temporal databases. And temporal databases play a very, very important role whenever we have to actually have these operations performed. And when the time series is very important, for example, that the data which has been collected, or a temperature data which has been collected for next, say for example, 5 hours, has to be, we have to ensure that data has the all the data has been covered. And obviously there is a time stamping of the data is also done, so that whenever we are going to retrieve the data, we are getting the proper data at and what actually we also, what we say in database language, we say that we are adding a metadata with this data. Now, obviously, there has to be a fast search and range queries, and that actually may be a disadvantage here, because whenever we have a huge data, obviously the searching, the fast search and range queries will obviously could be done there, because every whether it is an SQL then non-SQL database, that we'll be discussing later. But the fast search and range queries obviously will put a huge challenge on these databases. Obviously, there has to be a geolocation support, that's very important, and there has to be a real-time stream, and obviously there has to be a support for ever increasing data. And that will be discussing that how these if there is an ever increasing data, how these what you call as the uh, there is a vertical expansion and there is a horizontal expansion, that will be discussing in the slides, coming slides. Now, these are the key factors which are actually used for selecting the database for IoT applications. That means the number one is indexing size and scale. That's very important. Means the database should be highly scalable. And normally we talk of two scales that we'll be discussing. That's one is called as a horizontal scale and a vertical scale. And obviously there has to be a reliability. It has to be a user-friendly schema and convenience of operating. And obviously everything should have a query language, because unless and until we don't have a querying, whether it is a SQL or no SQL database, that whatever we are using, the things will become very complicated for us. And obviously there has to be some transactions and process modeling also, and heterogeneity has to be seen there, because normally when we talk of IoT databases, and they can be a centralized database, obviously they can be distributed databases also. And while these distributed databases can be a homogeneous type, they can be heterogeneous type, and they have to have these heterogeneity in the type of database and also heterogeneity in terms of data also. Both the things has to be there. And obviously there has to be aggregation of an archiving also. That's very important when you're storing. And these are the types of data that we actually normally have in IoT. It can be an RFID data, it can be addresses, what you call as, it can be descriptive data about the object device. For example, you have 20 devices, and how you are going to identify each device. Maybe there will be an ID or a device ID will be there, and by which you will able to understand that this data is from that device. And obviously that data are pervasive. These if say environmental data and positional data have we need the type of data also stored in the what you call as in IoT databases. There can be a sensor data, and the sensor data can have multiple dimensions. And there is an information about past models, some, and attenuators that control the data that is. And before going to these up to this, these are the challenges which actually IoT has. But actually, how we are going to cover this data, how we are actually going to put this data. Therefore, what are the various properties that these databases will have? The first that we need to understand, that means the benefits of relational databases. Means whenever we talk of relational databases, it was a concept that was given by Dr. E.F. Cord in 1970. And in this relation databases, he said that the data can be organized in the forms of represented in the form of tables, where data can be arranged in the form of rows and columns, where the name of the table will be the entity, the column definitions will be the attributes. The name of the every row of the data of the table will be a data field, and every column of the table will be a data field, and every row of the table will be actually a data record. And we have seen over a period of time, these relational databases have provided us huge. For example, you talk of Oracle, you talk of MySQL, you talk of all these companies. They have earned billions and billions out of it from these relational databases. Now, obviously, if you just go with the properties of these databases, and these databases are also used for what you call as IoTs. Means they are used IoTs where we need what you call as consistency in data, that we'll be discussing detailed later. Now they are designed for all purposes. They have acid properties, that is atomicity. They have consistency, they have isolation, and they have durability that already we know in databases. They have concurrency and recovery. Obviously, they allow what you call as locking, and we can have a shared lock. We can have a mutually exclusive lock, and obviously, if there is some problem, we can even end up in a deadlock. Now, obviously, it has a good mathematical background we need to have, because it is based on a set theory. And on that set theory, we are actually sort of arranging and saving and retrieving data. Now, obviously, it has a standard and structured query language, or a standard query language, that is SQL. And there are many tools which are actually associated with this, and these are the some of the what you call as an SQL databases that normally we use in IoTs, that is SQL Server, that is PostgreSQL, DB2, MySQL, Oracle. And these are the companies like there is Spotify, there is Netflix, what you call as Uber, and many other companies that are using it. Now, basically, when challenge arises when the data, because I have many slides, therefore I am going very fast, little bit faster. Now here, when we talk of RDBMS performance over what you call as data complexity, we see that obviously, say if you want to have a database for a salary list or some application for database application for a web app or something else, we will not see, we will see that okay, it is working fine. But when it goes to social network, location based services, for example, you have a GPS in the car and the data is continuously throwing, and there are say 500 or 2000 or 3000 or 1 lakh or 2 lakh cars moving on the road, and every car is using a GPS device, then you can see how difficult it is to actually cater that kind of a data availability, and how to take appropriate decisions on that data. Obviously it is challenging, and it is the beyond, it is obviously the beyond what you call the scope of these RDBMS databases, that is relational database. And there is another class of databases that is actually called as a NoSQL database. Now, NoSQL databases is now this class is actually called as an SQL databases, but here we are using a structured query language. But here it is not like we are not using a structured query language. It is actually not only SQL. The only thing between SQL and SQL, non-SQL database is that SQL databases have a proper schema, that a table, and then we have columns in the table, then we have records in the table, and we have to follow certain what you call as constants, whether it's a domain integrity, it is an entity integrity, it is an what you call as validity integrity, obviously it is a referential integrity. We have to ensure, then only we can actually put data into the table. And if you are not putting a data into the table, that record has to be kept as null. Means there are so many differences when we talk of no. Now here it says not only SQL. Not only SQL means, that means this is a no SQL database where we are hardly ever bothered about the consistency of the data. We are actually bothered about the high availability of the data, and we are bothered about the fast performance. For example, you have a Facebook data, or you have a data coming from these IoT devices, and obviously there has to be, and it can be a, it can be a big data also, and here it can be mix of both image as well as the text data. And normally in NoSQL databases, we the main thing here we need to understand, that means these NoSQL databases that we'll be discussing in the other page, they have actually two columns are there in that, because if you represent it in the form of table, it has only two columns. One is the actual data and one is the key value. And the key value is actually the, you can have it as a primary key, you can have it as a device ID, whatever you want to put, and rest of the things you can keep them separately, that we'll be discussing, and that is how you classify these NoSQL databases. Now here, if you just now here it is NoSQL database provides a mechanism that I already discussed. It is less constant consistency where you need, and here you say that no SQL systems means that it's not only SQL. They emphasize that in fact they allow SQL queries, means here we are using these SQL type queries that you are using. Now this is the difference, that there is an SQL database and there is a non-SQL database. When you talk of an SQL database, it has a relational makeup, means there are services which are provided by these. That, for example, you have data integrity, we have data manipulation, we have data display, we have so many things here. Obviously you have and then when you take this data, you go for OLTP, that is online transaction processing, and obviously you can go for OLAP, that is online analytical processing, where you can perform certain operations like OLAP operations, like you can first of all you can create data marts, then you can create a data warehouse, and then you can use that data warehouse for making certain decisions, and where you can, the way the schema you want to have a what you call as a star schema, you want to have a snowflake schema, any kind of a schema you can do in SQL database. But whenever we have NoSQL databases, you have, that we'll be discussing separately in this lecture, that is the, we can have a key values, we can have a column family, we can have a graph that normally we use in the Facebook, and obviously we have a document type of structure that we'll be using, and that normally we are using in what you call as a MongoDB. Now there is one important thing that is between the SQL and NoSQL databases. That is, whenever we talk of an SQL databases, we actually scale up, and whenever we talk of NoSQL databases, we actually scale out. What is actually scale up and what is actually scale out? Scale up is actually, say for example, you have a building, and what you are doing, you are adding a floor to the building. When you are adding more floors, say obviously your requirement is increasing and you are adding more floors to the building, obviously it will actually make a lot of tension on that foundation. Because normally, if the building has been made for 5 floors, you are making 10 floors. Obviously, the lower floors will have a huge stress, and even the building can fall. Therefore, there can be a sort of there can be an accident anytime, because you are scaling it vertically. But when you scale it horizontally, say you are making small flats, and you are making, therefore, obviously the tension, overall tension will reduce. But actually, in terms of data, how can we explain this? What is scale up and vertically, and what is scale out horizontally? Because normally in IoT devices, we'll be having more data. And normally when we talk of scale up and we talk of SQL databases, there is, hello, are you listening? Excuse me, is everybody listening? Hello,
Respond. Participants, please respond.
are you listening?
Yes, sir. Yes, sir. We are listening to your lecture.
Now here there is scale up and there is scale out. And whenever we go for scale up, that is normally in when we say we have relational kind of databases, we have an SQL databases. There, what we have normally, we have relationships, and when we have relationships, those relationships bind is the table together, because we cannot go out of the relationship. But here, when we say scale out, we actually go out of those relationships. Therefore, here, if we talk of there is we are normalizing it, then we have one to many relationship. We are
Room
uh,
number is
one to many relationship between the tables. Here we are. Hello. Here actually what we are doing here.
Rahul, do you have any query?
But here what we are doing, here we are doing in horizontal scaling. Horizontal scaling in the sense is, for example, if your disks are filled with data, you will get another disk and you will actually move it like that. And what will happen now, for example, your data is scattered over 100 disks. Now the big problem is how you are going to retrieve that data. Therefore, there what we have, we use what you call as we in NoSQL databases. Normally we use an hashing, and we have used a scaling function also, where actually we have given a specific number to every disk, and plus the ID of that record that you are going to store there, the data that you are going to store there is also stored with that. Therefore, directly going to that, so if you want to retrieve some data, you directly go to that disk, using a hash function, and then you directly retrieve that block of data which you want to visualize. Therefore, here if you go scale out, it is very much possible. Means by this we are able to store huge amounts of data, huge, whether it is petabyte, is zettabytes of data. We are able to store it in a very organized manner. But if you try the same into a single server or it will obviously create a lot of complications, and obviously it can even lead to what you call as a data crash. Now here, what is obviously we know that the relational databases are not built. What I was saying, that it is not built for distributed applications, because the joins are expensive. That is hard to scale horizontally, and impedance mismatch occurs, and expensive hardware. Obviously, whenever you are going to have a server, and then you have to increase the resources of that server, obviously it is going to be very costly, and the horizontal scaling has to be very it will be very easy. Now we see there are new trends which are coming these days, because normally what we have, we all are very familiar with these relational databases. But normally the new trends that, like, big data is coming, you have a huge connectivity, whether it is a connectivity of what you call as whether you are using a social media, or there is a P to point knowledge, and then there is concurrency, diversity. Obviously, you have a cloud grid. Therefore, the huge data is being evolved, and the processes that we already have, the primitive process that we used to have in these, they are now a big challenge is getting developed. Therefore, the people are skipping from SQL to actually NoSQL databases. Now, these are very important. Means whenever we talk of these as NoSQL databases, like you have a MongoDB, you have Riot, you have Cassandra, you have HBase, you have Couch, or anything Neo4j you have. So those databases are the what you call as an we say ideal databases where you have this IoT data, and they have certain characteristics like no SQL data. It avoids, that is the acid based transaction, means atomicity, that is overhead of acid transaction, because normally here the transactions are there, but they are not that very important while you have in SQL databases, because here the consistency of data is not that challenge, like availability is more challenge. Obviously the complexity of SQL queries, say for example you are retrieving data from more than one table, and when you are retrieving data from more than one table, you have also placed certain criteria like you have project, you have restrict, you are using restrict sort of operations by which you are saying that employee number should be greater than 60, or the city should be, so for example, Delhi, New Delhi. Therefore it is obviously creating a lot of, because when you have if the data size is huge, obviously these SQL queries will have high latency, and they will obviously uh, sort of decrease the efficiency of this database. Now there is what you call as a DBA presence, means you need not have a what you call as a DBA administration and obviously the transaction should not be handled in an application here. These are all the what NoSQL avoids. Now, obviously, there are certain advantages which include, that is, there is an easy and frequent changes to DB. That is, you have a fast development because they are all open sources and they are all schema-less. And when they are all schema-less, you need not to bother about the data record that you are putting in. Means it can support all kinds of data records that you are putting. It's not like say one variable is null and you are not able to show because it is violating certain integrity constants. Which here you need not to bother about that, obviously, and there will be an optimized storage also. Means that column will not be there. Means complete that row will be there, but it will skip that kind of an attribute without actually wasting the memory. Because in SQL, you have to specify whether you want to keep it null, you want to keep it blank, whatever you want. And if there is a data constant, then you will not be able to save it. But here you don't have the, and this way you can actually add huge volumes of data because normally it is schema less. That is the main advantage. Therefore, these things are the advantages where you actually accumulate data in one place without bothering about the schema of the table. Now, there is very important, that means when we are going to use these, what you call as, where you are going to use, when and why we use it. Say, obviously, you'll be using NoSQL databases where the traditional model is too restrictive. That means there is no flexibility in the schema. Therefore, when there is no flexibility, you are not able to change the structure of the table, or you are not able to put the data back into the table the way you want, because the maybe the data format has changed, or the data what you call as the tuples in the data have changed. Therefore, it is not storing. That means there you will use obviously the NoSQL, that is called the schema-less data. Now, the when ACID support is not really needed, means you need not have atomicity in the data. You are not doing some transactions which you want. You are not implementing any kind of a concurrency. You are not putting data in some isolation or something like that. It's not there. Durability of data is not there. Or what you can say, that you are not doing transactions where you are actually preserving consistency of data. You are least bothered about what, say for example, there will be an inconsistency in data. You are not bothered. That is not the big, it has to be asset. It's not like that, but it is not the only challenge. But if you say in financial data, that is the only challenge. For example, if the transaction means they will prefer that transaction should not take place, rather than, because it has not created any data inconsistency. Therefore, object to relational, that is impedance, that obviously that has to be that if it is there, then it is not a viable solution to RDBMs, because RDBMs, we say it's not made for, we know that it's not made for distributed databases, and it is not scalable by data. We cannot scale it much. And obviously you want to have a distributed resources. Means if you have a heterogeneous sources or distributed sources, your logging data becomes very challenging when we have these SQL databases. And obviously we have temporal data, that is the time based data, or the huge what you call as the data streams are coming. So storing the data is again very important. Now, the temporary data like shopping carts, wish list, session data, obviously they also are huge data. They also create, means when there are, for example, if you talk of Amazon or you talk of Flipkart or you talk of any kind of that data, to maintaining that users, maintaining 1,000,000, 2,000,000, 5,000,000, 10,000,000 users at a very time, and ensuring that their shopping carts and then their transactions is very difficult to manage. And obviously the data which demands flexible schema. For example, you have a data of an employee where the means you are providing data from the employee, where you are asking him to get your age, get your address, get your what was your the first salary, when you got the next promotion. But if you have a data, for example, and that data, for example, if the data is coming from an IoT device, for example, it is collecting the, for example, the blood pressure, and there are five, six tuples of that data, which are actually data parts, which are actually stored in that particular schema. For example, sometimes we get only two because of some problem. We are not able to get all five. Therefore, if you are using an SQL, the rest will become null. It will not be storing it. It will not store it. But in no SQL database, you will not have any problem, because normally you don't have a defined schema there. All the data will be accommodated there, because the availability of data here is important. Obviously, there is a there has to be a best data store depending on the nature of the data, that what I was discussing. And when we go for directly for financial data, that is data requiring asset compliance and business critical data, there we cannot use NoSQL database, because there we need to sort of the data should support, the database should support what you call as the asset properties. It has to be atomic in nature, that is all but none. What it has to be consistent, it has to be resolution, and it has to be durable. Now, what you call it, that what I was discussing, that means in relational databases, you can add record which does not fit into the schema. You need to add nulls for unused item in the row, that I already told you. Now we should consider data types. Means here we have to consider data, but in SQL database, there's only one data type you can put. You can put it as field value. You have to put it as strings, and under strings you can store all the data. Now, for example, you can't add multiple items to that field. Means for example, you cannot have a database based on the database of pertaining to the input data, because there you have to define a schema. Now here in NoSQL databases, there are no schema to consider. There is no unused cell. There is no data type implicit. Most of the considerations are done in application layer, and we gather all the items and aggregate documents. Now here, this is the relational model, and this is the NoSQL model. In the relational model, you have a table, you have a table one, you have a table two, and then you have a, for example, here you have one is to many relationship, or you can have one is to one, whatever relationships you can have here. Now here you have also the data types for that fields. That means, say if this is an integer, you have to put an integer here. If it is boolean, you have to put a boolean. If it is double, you have to put double. But when we have a NoSQL databases, we have here we are using one of the models, that is actually the document model. Here you can directly see that everything you are putting in strings. This is actually the what you call as an attribute, and this is the data value. Now here you are seeing ID is this, value is one, value two is this. Means everything. For example, here it has one is to many. There is items, and then there is some other value which has to be stored here. That can also be done. Means what can be achieved here in one is to many relationship can be achieved here also in a document-based method in NoSQL. Now here, when we talk of these NoSQL databases, we are actually we have four types. One is the key value, one is document, one is graph, and one is column. Now we will be discussing one by one. For example, I told you that there are only two values. One is key and one is attributes. In attributes, actually, you have what you call as an SQL as an attribute, and then you have a value. Means, for example, you see here 1, 2, 3, 4 values are here, but here what you have 1, 2, 3, 4. One you have 3, 1. You have here you have what you call as 1, 2, 3, 4, 5, and 6. Now here you have 6 values. That is here you are seeing here. That means when you are 6, that means how you are saying that how this table is taking this data, how this model is taking this data. It has only 4 attributes here, and it has 1, 2, 3, 4, 5, 6 attributes here. Now when it is 1, 2, 3, 4, 5, 6 attributes here, that means it is schemaless. Means here you are not using a particular schema. Here you are going out of the schema. You are storing these values, and this is also stored. And you can have millions and billions of records like that. And this can be put in one disk. You can actually continue in a horizontal. You can grow that disk the way you want to grow. Now here the grow the many disks like. Now here the main idea is obviously you are using a hash table. Hash table has two things. One is called as a key, one is called as a value. And based on the key, you are actually getting that value. Now access data values by strings are called keys. Data has no required format. Data may have any format. Means we need not to bother about whether this is, even if it is a picture also, this can take it off. Therefore, the basic operations are whenever we are going to insert a value, we have to specify a key and a value, because whenever we are inserting a record, we are defining a new key, we are defining a new value. But when you have a fetch, you need not to bother about the value. Then you directly have to fetch the key, and based on that hash function, it will directly go to that and it will retrieve the values which are actually associated with that key. And but whenever we have to access the values, for example, based on when there are queries and there are what you call as restrictions in the queries, when we have to have restricted operations on the queries, here obviously here the what you call as the efficiency of these models, obviously it comes down. Therefore, whenever we have such kind of data operations to be performed, obviously those, if they are really time critical or something like that, we need not to perform those operations on these kind of models. Obviously, when you have to update and you can delete it. Now this is columns. Here you are seeing you have a complete columns here. That's name and value. Now here it is, for example, it is array long. It is a key value. Is here in the previous we had, because the key is all string. Now here we can have different and actually these are the columns which are associated with this. These are the columns which are associated with this. And obviously this shows that, for example, this is a row ID and this is a row ID, and here we have a column family, means everyone is, it all belongs to this array long. Now the column is the lowest and the smallest instance of data. It is the tuple that contains the name, value, and obviously a timestamp. Now you see here, for example, if you have a columnar family, we were using a Cassandra NoSQL database. You see, say if you are using MySQL and it is a data stream and average writes are 300 milliseconds approximately, and read average is 300. If you are using, if you rewrite 50 GB of data here, you see it is 0.12 milliseconds and 0.15 milliseconds. Therefore, it is 15 milliseconds. Now you see here how read average obviously will be faster than the it statements here. You are seeing that is 15 milliseconds, and you see how these read and write operations have come down using these NoSQL databases. Now this is actually the graph theory what you use. Normally you are using here you have you can scale vertically. There is no clustering. You can use graph algorithm easily. Now here when you have graph theory, that means every node in the graph we have that is actually the which has the incoming edges, there are outgoing edges, and it can be weighted and non-weighted graphs. And based on that, you can also save what you call it in your data, and you can retrieve it faster using these graphs. Normally, if you see Facebook and Neo4j, these are one of the Facebook implements, and Neo4j is a very good model that we actually NoSQL database model that we use for using these graph kinds of. Now it is document-based model, and here, for example, here document-based model we can use what you call as a MongoDB. Now here also you have these kinds of here associations. You can see these are you are in a position to implement, that is one is to many relationships. Here again you are seeing the data is in the form of documents, and every document has a is actually defining a separate document. Now here what we need means whenever we have data coming from these IoT devices and they are distributed in nature, these are the four things that we need. Number one is fault tolerance. For example, you have data coming from many nodes, and if one of the nodes goes down, means it should not overall disintegrate the system, or the overall what you call as the overall efficiency of the system should not go down. It should be highly available, it should be consistent, it should be scalable. Therefore, these are the things actually what we want, but actually getting all the four at one place is actually quite impossible. And for that you have a cap theorem. That cap means there is consistency, availability, and partition. And this applies to what you call as a distributed network. And why this cap theorem says that you should have consistency. Consistency means whenever you are changing the data, means after changing the data, transaction is done, there should not be inconsistency in the database. Means the value, say for example, you needed 12, it should be 12, it should not be 13, or it should not be 11. Therefore, if you have 11 or 13 and the actual value was 12, therefore there is an inconsistency in the database. Now, availability. Availability means it should be available. Available in the sense, say if you are getting data from sensors and you are storing that into the database, it should be available. It should be stored. For any time you want to retrieve that data, it should be retrieved. It should be in a position to retrieve. Therefore, availability is more important. And obviously, there is partitioning, partition tolerance. So partition tolerance is same what I was talking about. That means say if one of the partitions or one of the nodes is there's a failure, and it should not allow entire system to collapse. That actually what I was discussing here is written here. That means consistency means that all clients see the same data at the same time, no matter which node they connect to. That means there is consistency. Availability means that any client making a request for data gets a response, even if one or more nodes are down. Other way to state is all working nodes in the distributed system return a valid response for any request without exception. And fault tolerance means that single node failure should not cause the entire system to collapse. Now these are actually, now whenever we talk of these NoSQL databases, now they it can be a CP. That means it is what you call as here we say this is consistent and there is a partition tolerance. In AP, it is availability and partition tolerance. There is CA, it is consistency and availability. Therefore, getting this, that is and based on that means when we have no SQL databases, you see what kind of IoT devices you are using, and based on that IoT devices, you have to see which kind of database will suit you. Therefore, you don't have to miss here. You need not to be sort of what you call as extra adventurous or extra selfish, and then maybe you will enter into a big trouble. Therefore, you have to ensure what kind of data you are getting from those devices and what kind of data you need to, and what are the various operations that you are going to, what are the various analysis or analytics that you are going to perform on that kind of a data. And based on that, and obviously what kind of models you are going to use on the data, that will, these database structure will actually define it. Now here, if you have a CP database, the CP database will have consistency and there will be partition tolerance. And there will be at the expense of availability. That's very important. Means the availability is not important here. Here consistency and partition tolerance is important. Therefore, it will be at the expense of availability. When you say AP database, it will be availability and partition tolerance at the expense of consistency. Therefore, there will be an AP database where you want to put. Now here, what you have here, it has to be very critical, means financially critical database, you can use it. But here, if it is not financially critical, you can actually have a partition tolerance at the expense of consistency. But if you have to achieve both, then a CA database delivers consistency and availability across the nodes. It cannot do, but here, what happens here? Now it cannot deliver on fault tolerance, because normally if the one system is down, obviously you cannot achieve these, because you have already at an expense of, because one is there is some error or the system or some node is down, obviously you will not be in a position to retrieve data from that. And obviously achieving a CA kind of a database design, it obviously will be very challenging and obviously very difficult. Now, this actually has a cap theorem. This is consistency and availability. Obviously, you will use an RDBMS. One is consistency and fault tolerance. Now, these are the NoSQL databases that you are using. And if it is availability and partition tolerance, then these are the databases that you are using. Availability means you are putting the database. I talked about this Cassandra, means you were putting the huge data stream was coming. The main advantage was we just had to read and write the data. We just had to read and write the data. Therefore, this was the best database, NoSQL database which suited us. This is the best database when you have consistency and part. And normally, if you see here, this part, if you see this part, it is very clear that here we are compromising on availability. Now here we are, availability is more important here whenever we have RDBMS. Therefore, when we have consistency and availability, there we can say we can use RDBMS, and here you can use MongoDB, here you can use other. Based on that, you have to say. Now this is actually relational and non-relational databases. Now here you have structured, it is unstructured, it is static, it is dynamic, it is vertical, Scalability is vertical. Here it is horizontal. It is structured query language. It is unstructured query. It's actually not unstructured, because normally we can say unstructured because we generalize it. But normally every whether it is a MongoDB, it is Cassandra, it is E database, or any other NoSQL database, they have a different sort of a query language. I mean, every have obviously if it is a temporal database also, it has every database has a different query language, and it is but here you see normally it is same structured query. Let's say if you execute queries on MS SQL Server or SQL Server, or there will be little difference. Maybe in project and restrict operations there will be a little bit different. The rest of the things are little same. Now, obviously, it is OLTP. It is best suited for its online transaction processing, and it is less considered, because whenever we go for transaction processing system, their consistency of data is important. Availability of data is not important. Therefore, OLTP support here, you'll get more, you'll get less. And support, obviously, it is great support. It is community, because it is open source, and it is at means this we can say it is in infancy, and it is growing every time, because it is an open source. People are more and more research is going on here, because normally we have not generalized it. We have every sort of every vendor of this NoSQL has kept it the way here. They have their requirements are there, but they have not generalized the things in it. And obviously you can say integrated caching flexibility also means there you have a rigid relationship between them. Here it is non-rigid. Now here we have to bother about ACID properties, and here we have to bother about the caps too. Now here it is auto elasticity. Now obviously here downtime in most cases. Now here there is no, it's automatic, because normally the what you call as the when we talk of these SQL databases, uh, obviously the administration it's required more, but in NoSQL databases normally the administration required is very less. Now here, if you just go with a SQL database, it is easy to use. Obviously, we have to make a good investment here, and obviously they have high performance workloads, good structured data, and it is time consuming to understand and design the structure of database. Can't be difficult to scale. Obviously, it is very difficult to scale, because first of all you have to have a very good database design, then only you can insert data into, because then you have to first define the schemas, and you have to actually make every data item happy here, then only you can put it there. But here you need not to, they are already happy, you need not to make them happy, they are already there. Therefore there is no investment in the model. Rapid development cycles in general faster than SQL, runs well on cloud, and cons is unsuited for interconnected data. That is why you have relationships among the data. Technology is string matching, which I was discussing, and can have slower response time. Now these are the some of the databases which are actually suited for IoTs. I have kept certain things here, because normally whenever we are taking data from these sensors, means this is again a new topic. Means when we are taking these data from these sensors, then what are the various phases, and what are the, for example, these we use gateways there, we use what you call as uh, ingestion, and then we have reporting. And obviously from the data acquisition to data reporting, there are so many operations that we perform on these data. And for example, you have there are suited for IoT in the sense that the first is it is InfluxDB. That is a NoSQL database that we have already discussed what are those. And obviously it has a huge indexing, and obviously it has a very important that is built-in interpolation for missing data. For example, it has a very good data pre-processing interface, which actually helps us in getting a data in a much defined manner. Now there is a CreateDB. It's a wonderfully most used what you call as the database for these IoT devices. And normally these databases are, this CreateDB is normally used uh, for making the use of this IoT database. IoT database, once you are storing the data, you are actually doing some work of the data also. That's why you are performing certain operations, certain mining operations or mission, whatever you want to do. And there's a lot of analytics that you can perform, whether it is an artificial intelligence based, it is whatever you want to do, you can actually implement those techniques which you want to do. Now, obviously, it has that is that is device to device database integration is there, and for that you use that is MQTT, that is message queuing and telemetry transport. That, and normally other databases are somewhat which which you have, that is the MongoDB, or there is the DB or SQLite database. Now here, these are all open source databases. This is MongoDB is a NoSQL database, and SQLite is an SQL database, SQL Service again SQL database, and MySQL again SQL database. And these are databases which are actually suited for IoTs, and based on the process which actually I discussed, whether it is a static or it is dynamic, or where you are using a data in a static mode or data in a dynamic mode or in a stream. Based on that, you are going to select this database, whether it is a NoSQL or SQL database. Thank you very much. God bless you all. If you have any questions, you can ask. If you have any questions, you can ask.
If you have any questions, you can post your questions by directly unmuting or directly posting in the chat box.
Because normally what we should conclude is, that means based on the IoT operations that we are doing, it is not like you have to directly select a database for the IoT operation that you are, or for IoT data. You have to first see what kind of data is being generated by that IoT device. And based on that data, you have to see whether we are going to select an SQL or a NoSQL database, based on whether we want, we are transaction specific, where we want to sort of ensure that there is data consistency, or we are bothered about the data availability. So based on that, you have to switch between what you call as an SQL and NoSQL database. In NoSQL also, you have to see whether you are in, the consistency is important, and the what you call as the partition tolerance is important, or what you call as availability is important, or partition tolerance, or consistency and availability is important. Based on that, you have to actually select the databases for your IT device. Thank you very much. That is actually the conclusion of this lecture.
I think there are no questions, sir.
Thank you.
Yeah. I once again thank you sir, for having your thoughtful session in this particular FDP. Thank you once again, sir, for
Thank you very much.
being in this. There is one question, I think, sir, in the chat box. Is there any database which is not suitable for IoT?
Now, every database is suitable for IoT. But the only thing is that when you have to optimize the operations which you want to perform, obviously there you have to make a selection. That's all there, because database is, what is database? Database is collection of interrelated data stored in contiguous memory locations. And when we talk of database management systems, it adds the set of programs that access this data. Therefore, every data, because here we are receiving data, we are able to store it in the database. But the only thing is that when we have to optimize those operations, we want that availability of data has to be there, or consistency of data, then we have to make choices. Because when we, so for example, storing data is no problem, because whenever we are storing data, it is storing. But whenever we are retrieving it, that time we come to know what actually has been stored. Because unless or until we don't retrieve it, we don't know what is. And when we retrieve it, obviously there we can see what were the limitations of the data which actually we store. Therefore, based on those limitations, we have to select the best data. So every database is good for IoT devices. Means whenever there is a programming interface, means all application programs, because whenever we have a sensor data, when we are receiving data, data can be received by any application. Any application can be used for receiving the data. Therefore, at backend, whatever technologies you are using, whether you are using whatever technology, whatever means it is, sky is the limit. You can access the data and you can store the data in the database. Therefore, for every data, for what you said, that all databases can store data, because the data form that is coming from those IoT devices, it can be stored anywhere. Because even there is one more thing. Say, for example, you have a data, like, for example, we have many streams. One is called as a binary stream, one is called as a what you call as a memory stream. One is called as, there are many streams of data. And for example, you want to store a picture. And if you want to have a picture data, the picture data is not enough for BMP when it is stored in the database. It is actually, this picture is converted into a binary stream. The binary stream is converted into a memory stream. Then it is stored in the database. And when we have to retrieve that from the database, again, it has to be in the memory stream. The memory stream has to be converted into the binary stream. And we have to get a proper container for that. Automatically, you can view that. If the container supports BMP files, you are able to view that file. Therefore, every kind of data can be stored. Every kind of data which a IoT device can sort of send, it can be stored in the database. Thank you. And in every database.
Thank you, sir. Thank you so much.
Thank you very much. Thank you very much. Okay, I'll log out. Huh? I'll log out.
Yeah, yes, you can leave now, sir. Okay, participants, we are done with this session. So next session will start after lunch. So hope you will join us soon, 2 p.m. onwards. Huh?
Thank you, sir.
Thank you.